Welcome back, everyone. Happy Friday. Um, this is our second to last lecture. We will be starting convolutional encoding, and I'm going to try and get as far as I can to give you a good introduction to what that is. But I think it's pretty evident that at this time that there's not enough time to have a proper problem set on error correction codes and have you turn it in and learn from it before the final exam. So, excuse me. What I'm planning on doing is releasing a problem set and then releasing its solutions immediately. So it's as if it would be assigned. You can try the problems if you like, or you can jump straight to the solutions, and then it just won't be graded. So I think that's a reasonable way to give you an idea of what an error correction coding problem set would be like. But especially because I don't know how deep we're going to get into convolutional encoding, I don't feel comfortable actually properly assigning it to you. If you take umbrage with that policy, you can let me know, and I'm happy to hear you out. Okay, are there questions in general? Anything I can help with towards the end of the quarter here?
I had a question. I know that credit and no credit, we have to submit by the 24th.
Yeah, that's right.
I'm just wondering, also asking in general, like, should we anticipate more grades to be added into our grade? Because I don't know, like, am I going to be failing? I want to, yeah.
I see. I've procrastinated enough so that it's actually become an inconvenience to you. So I don't think that anyone who submitted problem sets throughout the quarter is in danger of failing. I'll put that out right there. So I can't guarantee that when I'm done grading all the problem sets that everyone will have an A, but I would be really, really surprised that if you submitted problem sets all quarter, if you came to lecture, if you asked questions, that you'd be in danger of getting what I would view as a bad grade. Now, that doesn't excuse the fact that I haven't graded enough problem sets to give you actually any idea what your grade is, but I will spend Sunday grading, if that makes any difference to you.
Okay, thanks.
Yeah. Anyone else? All right, let's switch over to, and I'm back on the PowerPoint, so head over to page 22 of the slide set, please. So what we have been doing so far in this module has been called block coding. That is to perform our error correction bit stuffing. We present a block of bits and we do something to those bits, whether multiply them by a generator matrix or encode them as a polynomial and then multiply that polynomial by a generator polynomial. Whatever you're doing, we have been doing that in blocks. So we called them frames or blocks, doesn't really matter. But the data words were of finite length. The code words were of finite length. And so we can treat everything in these chunks. It doesn't have to be that way. In fact, you can do what's called convolutional encoding or continuous encoding, in which case the bits that you're trying to encode for error correction purposes have no end. It's convenient to treat them as having a start because you can kind of know where to start your convolution, but they don't have to end for you to start sending bits. So this has utility in a couple of different areas, but honestly, there's nothing stopping you from doing both, right? A lot of times you'll see systems that have block coding kind of on the outside, and then after the bits have been block coded, they're still bits, and you can do convolutional coding on those bits. So you can double team your correction codes. So let's get a sense for what convolutional encoding entails. I'm going to try and use the same kind of notation as much as I can between block coding and convolutional encoding. In particular, we're going to say that there are k data bits where k is growing, n coded bits where n is also growing, but we're still going to talk about the code rate as being the ratio of k over n. Other parameters for convolutional encoders include the constraint length and the number of adders in your convolution. So what I have here on the right is an example of a length 3 convolutional encoder. And so the idea, where is, come here, okay. We're going to have n blocks, or n please treat this as a shift register. So length n, shift register. And the number of adders is going to be 2. So here's adder number 1 and adder number 2. And students also always ask me about what this symbol is. This is so down here, this is a commutator. And the idea is that it's going to sample VK1 and then VK2 and then spin around and pick up VK1 and then pick up VK2, where K is going to increment between iterations, between cycles. Okay, so for each data bit that comes in, we are going to get out 2 coded bits. So that's because for each state of the convolution here, we are going to pick up 2 output bits. So we talk about the rate as still being defined as k over n, but that doesn't make a whole lot of sense anymore, or it can become ambiguous because k and n go to infinity. So what you'll see is that this is approximated by 1 over L. So yeah, that's the idea that for each data bit that comes in here, we get 2 things out of here. Okay. Okay, so let's do a quick example using this convolution. So, and just for starters, I'm going to use a finite string of bits, so 1, 1, 0, 1, 0. Things to note are that the shift register is typically initialized to 0. Initialized. And then the first data bit then populates in this picture, the box on the right. And then what these 2 mod2 adders are going to do is they're going to draw from the registers from which the arrows indicate, and they're going to XOR all of those things. So this is 1 equals 0 XOR 0 XOR 1, and this one is 0 XOR 1. So the adder on the left has 3 inputs, the adder on the right has 2 inputs. And so for the first data bit, our output stream has 2 1s picked up from this commutator. All right. And then we shift the data bits in, and now we're taking these additional XORs and we're putting out a 0, 1. So this came from, you can think of this coming from the first data bit. This one is kind of like coming from the second data bit. And then we keep feeding in bits into our shift register. But it's important to note that the same data bit, so 1 and 1 here, they produce different coded bits because there's a history that we have to account for. Right? So this data bit of 1 gave us a double 1 in code word. This data bit of 1 gave us a 0, 1. So it's not like every data bit maps to the same code bit. We have the history of bits to consider, which is going to be both a blessing and a curse. I would say more of a blessing because it allows us to do more intelligent decoding based on the history as well. Okay, let's run through this example. I think we've got our 4th bit has been input now, and now our 5th bit has been input. And what showed up here is 0 padding. And these are important because this bit right here is our last data bit. But I'm making all this fuss about history, and so we would like to fully encode this bit. We need it to go all the way through the shift register. And so because there are 2 spaces that I need to shift it into, I'm going to pad the input data word by 2 zeros so that we're sure that this last data bit can make its way all the way through. Okay, so that means this example is a little bit longer than it ought to have been otherwise. And again, this 0 padding is not necessary if your data bit stream is continuous. If it's all data bits, then there's no need to worry about the end of the data bit stream. Okay, so at this point, we have encoded all 5 data bits. We have padded that. I think it's important to see that we've effectively padded it on both sides. Remember, we had 0, 0 from the initialization, and then 0, 0 from the padding. So what we have here on the output stream is going to be has shown that effect as well. If you initialize to different states of the shift register, you'll get a different code word. But I think it's a reasonable thing to assume that all of our shift registers start from a 0 state. Okay. And so what we got here is an example that the number of code bits, there's no reason that should go. Let's extend that underbrace all the way around. We're going to get the length of the shift register plus the number of data bits minus 1 times the number of bits per commutation, so L. And so if the number of data bits that you're encoding is much bigger than your convolutional length, than your shift register, then the approximation that one can make is that the number of code bits is approximately the number of adders times the number of data bits, which is where I got that 1 over L code rate from. Because if you divide both sides by n and both sides by L, this is where you get k over n approximately as 1 over L. Okay, and that approximation is good if you're encoding lots of data bits relative to your shift register length. Questions so far? Okay, I'm going to switch to presentation mode because I have an animation that I'm quite proud of in the next slide. So let's see.
Could I ask a question actually?
Please.
I guess you'll probably, what does this output stream necessarily mean now? Is it just,
So at the end of the day, every error correction code is a way to send more bits than you need so that if some bits get flipped, you can correct for them. So before it was like a linear block or a block that was a linear transformation from data bits to code bits. This is still a transformation from data bits to code bits, and there are always more code bits than there are data bits. And the idea being that you can now tolerate some of these code bits being flipped, and at the receive side, you can correct for those errors. So that is the same theme.
Okay.
Yeah.
I
haven't told you how to do it yet, like how to undo a convolution, and that's
okay.
what makes these a little bit tricky.
Okay, thank you.
Okay. How does this work? Okay, let's make you small. Can I get a thumbs up from someone or a yes that you can see the slide?
Yep.
Good.
Okay, great, thank you. So another way to think about these convolutional encoders is with a state transition diagram. So I believe you've seen these in your CPE classes, but I will go over it just a little bit. So the idea is that every input data bit generates a different set of code bits depending on the data bits that came before it. So for example, I'm looking pointer options, laser pointer. I'm looking here, and the state of the system is not described by the input, but rather by the former inputs. So in this case, for a big N equals 3, we're going to say that the state of the system is the previous 2 data bits. And because the previous state is length 2, that means there are only 4 previous states, which I can draw in a little picture here. So I've labeled these states as A, B, C, and D, just so I don't have to keep saying zeros and ones. It's a little bit easier that way. But we'll call state 00 A, and we'll call state 01 B, et cetera, et cetera. So the 4 states are represented by the 4 corners of this diamond. And then the way to read this figure is on every transition arrow here, there is a bit and then a slash and then 2 bits. And so the way to read this is the bit to the left of the slash is the input, and the bit to the right of the slash is the output. Okay, so for example, from state 00, in the last slide, the very first data bit was a 1. And so what this convolutional encoder will do is it goes from state A, and an input of 1 means we have to transition to state B. Also, we're going to output 11. Okay, so I think that's what what's going to happen when I tick this. Okay, yeah, so the big blue dot represents the current quote-unquote state of the encoder. We started with 0 state. Yeah, look at that. And then we transitioned to state B, so then the output would be 11. The next input bit was a 1, and so I think we're going to transition up to state D, and we're going to output a 0, 1. And then I think the next data bit was a 0, so we're going to follow this path over to C, output 0, 1. And the next data bit was a 1, so now we're going to cross over back to B, output 00. And then I think the next one was a 0, so we're going to output 1, 0 and transition back to C. So now I think we get to the padding part, so we're going to input a bunch of zeros, output 11, and then another input of 0, back to state 0. So eventually we're going to just keep cycling back to A and output all zeros. Okay, so this is my animated state transition diagram. You can tell why I wanted to show you this. It took a long time. One of the advantages of thinking about your convolutional encoders, right? So it's the exact same system that I showed you before, except now there's no shift registers. It's just a state transition diagram. One of the advantages of representing it this way is that there's no penalty in starting kind of midstream, right? As long as I know the state of the encoder, then I can just land on one of these A, B, C, or D, and then just keep going from there. So there's no real notion of starting and or stopping. You can just pick up midstream. All right, I think that's all the animations I have for you. So if we go back to this slide, just to take a view of the entire coded string of bits, the question now becomes, I mean, if you are comfortable with the encoding process, now we have to talk about the decoding process. But I'll pause here for questions on that. So in order to decode these kind of infinite strings, you could take the position that you're going to compute what every possible set of data bits would generate, and then measure in a bunch of code bits that you receive, and then pick the closest data bits to those code bits that could have generated that. So this is a little bit like blocking up the convolutional encoder to treat it like a block encoder. And that's roughly what we're going to do, but we're not going to enforce kind of strict, hard block edges. There are a couple of points of view here. So one of the benefits of convolutional encoding is that we don't have to make hard decisions anymore. And I think that's one of the biggest differences between convolutional and block codes, is we can do what's called soft decoding. So, and what I mean by this is there's no longer a deadline per se that at the end of the block we have to make a hard and fast judgment. This is the data word that I think was sent. I acknowledge the existence of other possible data words, but I'm going to commit fully and in a hard sense to this data word. So remember before, you had the idea that you could talk about the Hamming distance. So this is versus hard decoding. So let's talk about this Hamming 3.1 that we had before. So this was the idea that we have 3 code bits for every data bit. And 000 and 111 were valid code words. And the idea was that because we have a Hamming distance of 3 between valid code words, so to get from 111 to 000 requires exactly 3 bit flips. So 1, 2, 3. That's our Hamming distance. So D between the only 2 valid code words was 3. This means that around every code word we can draw a Hamming sphere of radius 1. So for example, if we were to receive this code bit, this string of code bits, because it's closer to 111 than it is to 000, then a hard decoding would say this, we're going to decode this as the code word 111, which maps to data bit 1, say, and then go to the next set. A soft decoding in this context, in the block coding context, would mean something like we can have the same coding setup. So same cube. But now, if we were to receive this bit, or this string of code bits, now we would then say, code word is going to be 111 with probability 2/3 or something like that, and 000 with probability 1/3. Actually, it would be probably more like 90% and 10%. But this is with every possible decoding option, we associate a score. And I listed them as probabilities, but you can just think of them as scores. And then you can send these scores to the next subsystem. And that subsystem, if it's equipped, it will take into account those scores when it's trying to decide what data bits were sent. Okay. Now, from the soft decoding, you can always recover hard decoding because it just means pick the highest score and forget the rest. But the idea behind soft decoding is that if you don't have to, why commit to a single choice? You can pass this information on to the next subsystem and let it make its own decision. Because maybe the next subsystem, it wasn't expecting a 1 data bit. Maybe it was expecting a 0. And so it might be prudent to say, well, let's admit the possibility that it could have been a data 0 bit, rather than just saying, oh, outright, we're going to take the maximum likelihood result. And so what that leads us to, this notion of soft decoding, is this Bellman's principle of optimality. And the idea behind Bellman's principle is that if you were to start in this string of decisions, regardless of what has led you to that position or that state, then an optimal policy must still be optimal if you continue it from that point onwards. So let's talk about this a little bit. The way I like to think of it is kind of traversing a map, or finding the shortest distance between two places on a map. So if I want to get from point A to point B, and let's say that I have an algorithm or some way of deciding that the optimal way to get from A to B involves this motion on this map. Okay, this is where the highways are, or if the other way has, you know, dungeons and trolls or whatever. But let's say that this is the optimal path from A to B. Okay, so this is something we're assuming we know. What Bellman's principle says is that if someone after this fact comes along and says, hey, can you tell me what the optimal path from C to B is? You don't have to do any more work. The work has already been done because C lies on the path, the optimal path from A to B. This must be the optimal path from C to B. Okay, so the idea is if you start midstream of something that was optimal before, the fact that you're starting midstream doesn't change that it's optimal. Now, Bellman's principle is one of these things where when I say it like that, you wonder why did anyone get their name attached to this kind of obvious statement? But it has pretty significant implications because of what's called, it's used a lot in dynamic programming. So in dynamic programming, the way that I stated this, you actually flip it on its head. And this is basically what we're going to be doing for the rest of the lecture, is we're going to be saying, if I can build, and so maybe we should do this one more step. If out of 3 points here, say D1, D2, and D3, if I look amongst D1, D2, and D3 and find that the quickest path between all of those is this one, and then I consider how to get to D1 between maybe E1, E2, and E3, then if my end goal is B, then I only have to judge how to get from the E's to D1, and then I know that to get from D1 to B, I've already got the fastest path. Now, how does this translate to soft decoding? This is more like we're going to give this a score. So this is, path 1, and this says score path 2, and this has score path 3. And so now, if I need to get from the E's to B, if I have to go through, say, E3 to D2, I already have that tabulated, the cost to get from D2 to B. This is commonly referred to as the cost to go from one state to another state. Okay, so Bellman's principle, when I first encountered it, it seems, I don't know, trivial it feels like heresy, but it feels obvious to me, and I want it to feel obvious to you, and I want you to wonder why anyone would like write a textbook about this. So do you have that question? Or is the principle itself still unclear? Okay, so no one's speaking up. Maybe Jack's typing, and I always ignore him. We'll assume that that's happening. So let's move on to how we introduce dynamic programming and Bellman in decoding convolutional encodes. So let's switch back to, we're going to have our animated blue dot again. And so what I'm going to do is I'm going to go through this encoding process again. And now I'm going to use the Trellis diagram to help me decode it as well. So again, so one more time, we are encoding the same data bit example 11010, and I'm now presenting it in a third way. So I showed you the convolutional shift register, I showed you the state transition diagram, and here what I have is called a trellis diagram. And what it is, it's basically a state transition diagram, but smeared over time. So now time is explicitly left to right in this diagram. And so what we're going to do is we're going to start from state 00. So that's our 0 state. And the first data bit was a 1. So we travel on that branch and we output 11. The next data bit was a 1. So we follow this, and now we're in state D. So now the vertical position on the slide corresponds to what state we're in. And then the next data bit was a 0. And then the next data bit was a 1. And then the next data bit was a 0. And then the next data bit was a 1. Or was it a 0? No, sorry, it was a 0. Because, let me see if I can get the pen. Pointer options, pen. Okay, so the data that we're trying to encode was 1, 1, 0, 1, 0, and then we pad with zeros. Okay, so I think we traveled this branch, and then the 1 branch, and then the 0 branch, and then the 1 branch, and then the 0 branch, and then based on the padding, we end up here. And you'll note that when 0 is input to state A, we stay in state A. So this would be then all state A forever onwards if we had no more data to send. So again, this is exactly what we had in the state transition diagram, but now time is more explicit. Okay. So let's see here. What we're going to do is we're going to use a Trellis diagram, and we're going to basically go backwards on it to decide, given a state of received bits, what is the most likely sequence of data bits, but with the possibility that we can make mistakes along the way. That's basically the long and the short of it. Questions on this? Okay, so I said it was called dynamic programming when in the context of decoding convolutional codes, it gets the name the Viterbi algorithm. So that's what you're going to see here. And the basic idea is that we keep scores for every path along the way, for every possible way to get to our current state. And so this is what we've got here are, so now we're at the receiver, and these are our received bits that we're getting in. And so the receiver has the same trellis that the encoder does. And so what it can do is it can say, if I know that the state started as 00, So that's an assumption, is that we're assuming to start here, start at A as an assumption. But I receive a 0, 1. That's not possible. Why? Because if the data bit were a 0, I should have received 00. If the data bit were a 1, I should have received 11. However, in our very first set of bits, we get an error. Okay, bummer, but that's kind of the whole idea of a error correcting code. So what we're going to note in these boxes are the number of errors required for the received bits. So because we received 0, 1, that means that one of these two bits must have been flipped. So both of these paths get a score of 1 at this point. Now I'm going to do the next stage as well. So in the next stage, we look at each of the possible. So these are our new possible states. And the errors required, the number of errors required to get to those states. So from each of these possible states, our Trellis diagram says that we could go to, well, all 4 possible states. So from state A, if the data bit were a 0, then we should have received 00. Instead, we received 0 or 10. So that means that we would add 1 to our score. If we were in state A, so there's a bunch of presuppositions here. If we were in state A and the data bit were a 1, we should have received 11. We didn't. We received 10. So that means add 1 to the score. Oh, and if in case it's not obvious, because we're counting the number of errors, we're going for golf scores here. Lower scores are better. Okay. Let's do the other supposition. If we were in state B at this point, and the data bit were a 0, then we should have received 10. Oh, look, we received 10. So add nothing to the score remains the same from 1 to 1. If we were in state B and the data bit were a 1, we should have received 0, 1. We received the exact opposite of that. So this would require 2-bit errors to transition from B to D. Now, we're not deciding anything yet, and that's crucial. This is what I mean by soft decision making, is we are allowing more data to come in until more data doesn't actually help us determine what happened, and then we can pass our decision on. So questions on these two, because it's going to get, the screen's going to get fuller, and I'm going to be able to annotate less. So I want to address questions sooner rather than later. So if we were to quit right now, if the receiver was, say, only expecting 2 data bits, then the most likely scenario would be a 1 and then a 0, because the path with least score follows this, which would have been a data bit of a 1 and the data bit of a 0. That's, at this point, if we were to quit, that would be our most likely decoded sequence. But let's press on. So in stage 3, we are here. And if we were in A and the data bit were 0, we would have to add 2 errors because we received 11. But now that we could have been in any state, it gets more complicated, because there is another way to transition in this point in time to state A, and that's along this path. So there are 2 ways to get to state A in this time step. One is from A, which would require 2-bit errors. One is from state C, which would require 1-bit error. sorry, no bit errors. Let's make this a little bit neater. So this notation is supposed to live on that adjacency. And so that means that to go from C to A would require 0 bit errors. And so what we're doing here in this minimization is the 2 from the prior state added to the 2 required to go from that state to this state versus the 1 from the prior state added to the 0 required to transition from that state to this state. And that is why the most likely scenario out of these two is to transition from C to A. And that statement is cannot be made in isolation, because to get from C to A, we have to account for the cost to have gotten to C and A to begin with. So let me erase this and we'll start anew. So the score for state B, well, there are 2 ways to get to B. And this is where having the Trellis diagram handy on another page comes in handy. The ways to get to state B are either from A or they are from C. So from A 1 data bit means a double 1 code bit, which is exactly what we received. So this means add 0. That's that 0. From C, a 1 data bit means a double 0, which means we'd have to add 2. And so now the cost to get to state B at this point is going to be 2, because we're going to take this as the minimum. Okay, that operation continues. And here I think we made it easy because it's always, there's no ties. So we'll address what happens when we get to ties in a bit. But the min between 3 and 4 is clear. The min between 3 and 4 is clear. And so we have definitive scores for all of these states. Questions on this? Have you, I guess, is the reason you're not asking questions because this is obvious, like you've seen it before? Or what?
It
What happened?
somewhat makes sense.
Well, we process.
No, you must process faster. So yeah, basically what I want to know is, have you seen this before? And if the answer is no, then I understand why you're not asking questions. If the answer is yes, then I also understand why you're not asking questions and I can go faster.
I feel like I've seen something really similar before. I'm not sure if it was Trellis diagram though, but the concept, like, I kind of get it. Yeah, I feel like it rings a bell.
I'm somewhat recognizing the pattern.
Okay.
I think that's in some sense.
Okay. So let's do one more. No, we're gonna do a bunch more. But now there's nothing new in the zoo. It's all wash, rinse, repeat. We are only ever going to be comparing 2 ways to get to a state. And let me actually go back to the original Trellis diagram and talk about why that is. So if you were to look, say, here, at every dot, there's only ever 2 in arrows. And that's why in our decoding operation, we're only looking at the minimum between 2 things. In a larger state, like a larger state system, then you would have more input arrows to every state, and your minimization would have to be over more numbers. Okay, so let's see. Let's pick an interesting one. Well, actually, yeah, this one's kind of interesting. So in order to get to state D at this point in time, so stage 4, I'm calling it, we received a 1, 0, which would mean no bit errors from state D, so that's this line. Or it would mean, what's the other alternative? So to get from B to D, Here it is. A 1 data bit would require 2 bit flips. So I think I have this. This is a typo. There's no way to get 3 errors here. So that's a typo. It should be 2. Fortunately, it doesn't change the result because 3 plus 0 is still smaller than 2 plus 2. But that's important to, like, as long as you keep your arithmetic in the right column. This first thing is the old score, and this second thing is the errors required to transition. So it's impossible to have 3 errors, and you're only sending 2 code bits for every data bit. So that's why it was pretty evident that this had been a typo. And the reason that it's 2-bit errors is because we were expecting 0, 1 if going from B to D, and we receive 1, 0. Okay. All right. So moving on to the next stage, and I think this might be, no, this is not quite it. Same process. We're comparing the cost to get to the previous stage to the cost to get to the current stage. And we work out that now it's actually kind of narrowed down. There's lots of states with 2 and lots of states with 3. But once we end up 0 padding and we can say that we are done in some sense, then we pick the quote unquote final state with the least weight or the smallest score or the best golf score. And then we say, what was the path that we took to get here? So what I'm doing is I'm keeping notes, I'm keeping tabs, if you like. The solid arrows in these previous slides represent the path with the least number of errors. So that's why I've been keeping track of that. And what I'm doing is I'm, from this state, I'm looking solid or dashed. I'll take the solid one. From this state, solid or dashed. I'll take the solid one. From this state, solid or dashed. And these solid or dashed meant the path that gave me the better score. Solid or dashed, take the solid one. Solid, there is only one path here, so we get to follow those for free. So I probably should have highlighted that a little bit more. Let me go back, say, to this slide. And for example, at this state, I'm looking at this 2 plus 0-bit errors, so 2 plus 0 versus 2 plus 2. And this 2 and 0 is from the A to A transition. And this 2 plus 2 is from the C to A transition. And between these two, this is the least, which means this one gets the solid bar. Okay. And again, if we had a larger state space, then there would be more dashes, but only ever one bar, provided no ties. So this is where, if there were ties, you would have multiple solid transitions into a state. And then you would have to compare on the way back which of the two gave you the better result going backwards. Okay, so now that we have this least cost path, then we can say the data bits, so the decoded data bits was 1, 0. I think it's this one, 0, 0, 0, 0. Okay. So what else can we learn from this? Oops. Chat box. Got it. What else can we learn from this is you can start decoding too early, but there's no point in holding off on decoding after a certain point in time. And that threshold depends on the size of your state space. So because we had n equal to 3, after 3 stages, I get no more information about the previous bits that were received. So if this were truly the signal that was sent in, the data that was sent in, this data bit only lives, quote unquote, lives in the convolutional encoder for at most 3 stages. So 1, 2, 3. After this point in time, the system has no idea what this data bit was. And so we as receivers shouldn't garner any more information about that. So I think that a lot of times I present this as being a continuous thing, and then I say, oh, here's a discrete data set, and we wait until the very end to decode it. But that's not true. Is we could have started our decision about 1 after this point in time. Okay, because the 1 doesn't live in the system at any point after that. Okay, we will talk some more about this, and I will be happy to answer questions that you have on Monday. But yeah, I think we're out of time now. Cool. Thanks, everyone. Have a good weekend.